Hi there, my name is Ron S. Friedman. I'm an IT professional and a science fiction writer. Welcome to Sci and Sci-Fi, connecting the public to science and technology through storytelling. Today, we have a special surprise for you. Last month, NASA Administrator Jim Bridenstine gave a presentation at the International Mars Society Convention. During his presentation, he responded to a couple of questions from the audience. One of those was a question I submitted. I will share his answer with you, which of course is related to today's topic: rotating spacecraft and artificial gravity. But before we proceed, please don't forget to hit the like button and subscribe to the channel. That will really help the YouTube algorithm help others find my channel and thus enable me to produce more content. You may also want to consider check some of my books, links will be added below. Now, let's proceed with the presentation. Rotating spacecraft and artificial gravity. On the image to the left, we see Jim Bridenstine, NASA administrator, and on the image to the right, we see an image from the 2001 Space Odyssey, where a spacecraft en route to Jupiter is generated artificial gravity through spin. Spin is one of the best way of generating artificial gravity. We'll talk a bit about it a little bit later. But before we do that, let's examine what happens at microgravity to the human body. In microgravity, like for example on the International Space Station, the gravity is zero or very close to zero, and this is not where we evolve. We evolve on Earth at a 1G gravity. Our physiology is adjusted to 1G gravity. This is what's best for us. Now, if we are to move into space and we don't generate artificial gravity in some way that simulates gravity similar to Earth, then it's going to impact our health. One of the things that's going to be impact is bone loss. We are going to lose between 1 and 3% of our bone mass. That means our bones are going to become weaker, more easier to get to fracture. Another thing is our vascular system, our heart. Here on Earth, when we sit up straight, we walk, the heart needs to work hard in order to pump blood to our brain. In space, it's like lying down. It's easy to pump blood to our brain, so the vascular system and the heart is not working that hard, and therefore they become weaker with time. Another thing is muscle loss. Since our body is not exposed to gravity, it's very easy to float around. Our muscles are deteriorating. Of course, if you're on the space station, you are required to work. Astronauts are required to work at least 3 hours a day and do exercise to strengthen the muscles. So that do prevent some of the muscle loss. Of course, they cannot work all the muscles; they work some of them, and it's not exactly as Earth. So it does enable the astronaut to be healthier for a longer time in space, but it's not an optimal solution, and it's not a permanent solution. Other things is a cranial pressure on the brain, which may cause permanent damage, including permanent damage to the eye and the eyesight. On the image to the right, you see Misha from the Netflix TV series Away. He's a veteran astronaut. Of course, because he had a lot of experience, he's been in space a few times, his body already accumulated some damage. And when he started the mission for Mars, he was selected because of his experience, but because of the damage to the body, very right at the beginning of the journey, he started to lose his eyesight and started to become blind. And that's not very good if your most experienced astronaut is becoming blind. That's not very good for the mission. It's also not very good for the astronaut. Well, that's what happened. Just for the record of staying in space in microgravity in the International Space Station is 437 days. That's more or less the maximum that the human body can sustain without causing permanent damage or too much permanent damage. Maybe it could be a little longer, but we can see that there is a problem. Additionally, microgravity is inconvenient. I mean, I read an article not too long ago that NASA new $23 million space toilet was launched to the International Space Station. You can imagine how complicated it's going to be to use such a device. It's much easier to do it all you need in zero gravity. It could be very messy with zero gravity. Try to imagine if you eat, if you have a plate and your food start to float around. So there are ways to go around it, but it's pretty messy. And of course, if we can generate artificial gravity, it would be a better choice. Spacecraft with microgravity in science fiction. On the image from the left, we see the Avalon from the movie Passenger. It's not exactly like a wheel, it's more like a seed. And the passenger and the astronaut or people in this spacecraft are living on the edge of the spinning things over there. But it's still spinning and they feel artificial gravity as if they are on Earth. The image on the top is the Hermes, top right is the Hermes from the movie The Martian. The role of this spacecraft is just travel from Earth orbit to Mars orbit and back from Mars orbit to Earth orbit. During this time, instead of living in microgravity, the astronauts are living on the wheel in the center. It has like 4 cabins. And while they are in the cabin, of course, they because of the spin, they feel full gravity, and it's improve their health and conveniency during the voyage to and from Mars. The last picture at the bottom is the atlas from the Netflix series Away, the one we spoke about earlier. Again, it has 2 cabins, then spinning around the center, generating artificial gravity for the people who live at the cabins. Of course, if they travel to the center, again, they will experience microgravity, so they only do that if it is required. But for most of the voyage, they will spend their time on those cabins in full artificial gravity with all the health and conveniency benefit. So the idea behind how to generate artificial gravity through spin is basically centrifugal force to simulate acceleration. It's like a carousel in an amusement park. If you've been to a carousel and you were spinning around and you feel that your back is pushed against the wall, this is exactly the same principle. So we can generate more gravity or more artificial gravity by 2 ways. One is to make a bigger wheel, spin it at the same speed but a bigger wheel, or we can spin the wheel faster. The faster we do, the higher the gravity is. Now, typically, a bigger wheel that spins slow is better because then it will be less noticeable. The Coriolis force will be less noticeable, and the human body will feel less disorientation. So, to generate 1G, a big wheel spinning slow is better than a small wheel spinning fast. The next question is, of course, if artificial gravity is so good, why haven't we done it already? In real life, we actually did do it. In September 12, 1966, Gemini 11 performed a rendezvous with a Agena target vehicle. It's an uncrewed vehicle. It's an early stage to simulate the Saturn V. So the Gemini 5 connected to the Agena vehicle using a tether or a cable, and they were spinning around each other on the center of mass of 2 vessels, generating artificial gravity. Of course, it wasn't for a long duration, and there was some engineering problem, it caused some damage, but the principle has been proven, and we were able to indeed generate artificial gravity in space, even if it's not full G and it's not for a long duration, we are able to do it. So we know how to do it, we know it's possible. And how did I find about it? Actually, I didn't know about it until I spoke with Mike Moulin, an astronaut, and at the bottom here, when he gave a presentation, at the bottom here is a picture with me and my wife with him when we visited Cape Kennedy in 2018. And now we're going to the moment we've all been waiting for, NASA Administrator Q&A.
Thank you so much. And I think we have time for one last question from Ron. He would like to know about the challenges of long duration crew missions in microgravity. And are there any proposals for a rotating spacecraft with artificial gravity? And if not, how can someone submit a proposal to NASA for that?
Yeah, that's a great question. You can certainly submit unsolicited proposals to NASA. You would do it through the Human Exploration and Operations Mission Directorate. If you want to do a technology demonstration, you would do that through the Space Technology Mission Directorate. As of this point, we don't really have any plans to send, rotating kind of architectures to Mars for the purpose of creating artificial gravity. I can tell you, I've read the case for Mars, and I understand, Robert Zubrin's vision for, spinning, a rocket body and tying it to the capsule and spinning them with a cord attached to them, and it creates just enough. It's a wonderful concept. There's probably room for that kind of technology demonstration, I would imagine, for sure. I think probably maybe not a better approach, but a different approach that we're working on every day is just going faster. So it's not just the microgravity, it's also the radiation. So the harmful physiological effects from microgravity and radiation are pretty damaging to the human body. But when you get to Mars and you're on the surface of Mars, the microgravity is largely mitigated or offset, or the countermeasure is the 1/3 gravity of Mars actually provides a lot of countermeasure to the problems of microgravity. And when you're on the surface of Mars, the radiation dose is cut in half by the simple fact that the radiation is only coming from above, not from below. So getting to these other worlds faster is more important than probably anything else. And the moon would be the same way. Being on the gateway for long periods of time, probably a lot more damaging than being on the surface of the moon, or even under the surface of the moon, being on the surface of Mars, or even under the surface of Mars. So I think if we can get there faster, that's a key enabler. It also enables us to be able to explore further within the solar system itself. And I would think one of the ways to get there faster is nuclear thermal propulsion, which we do have investments in, and then nuclear electric propulsion, which we also have significant investments in. But you're right, the human physiology is not designed for microgravity or high doses of radiation. It does, you lose 1 to 3% of your bone mass every year. Your vestibular system gets all messed up. Your ability to fight off disease, your immune system gets really messed up. There's all kinds of cranial pressure in the brain, and that affects your eyesight, could be permanently. The key countermeasure to this, though, is to get to another world. And that other world, of course, in this case would be Mars, because that is having the gravity well of Mars would be a key countermeasure. The quicker you get there, the more you reduce that exposure. So with that, I'll close out. I know I'm over my time. I just want to say thank you to the Mars Society. Thank you to Robert Zubrin for your advocacy, your very thoughtful writing, and the great work that you have done to help kind of focus NASA's mission where we can get it focused. And we will look forward to the great things that this group does in the future. So it's great to be with you.
Thank you so much, Administrator Bridenstine. Have a wonderful weekend.
You bet. You too. Bye-bye.
I hope you enjoyed the talk. Here's a recap of Jen Bernstein's presentation, answer to the question. Basically, what he's saying that gravity, microgravity is not the only concern. It's not the only health issue. Another big health concern is galactic cosmic radiation, or also solar flare. So these two types of radiation and microgravity is what preventing a long duration space voyage because of the health risks to the human body. So additionally, artificial gravity is a complex engineering solution. Therefore, although it is a good idea, what NASA is focusing right now is to go faster to Mars. Instead of building artificial gravity that may indeed solve the issue of microgravity, but not solve the issue of radiation, they want to go faster, thus reducing both risk of microgravity and radiation. So how is NASA planning to do that? Using nuclear propulsion. The image you see here on the right is from the Orion project. It was a project from the 1960s. It was canceled in the early 1970s for various reasons, but basically the Orion project was to blow up nuclear bombs behind the spacecraft that will push it forward. And of course, if you want to launch such a spacecraft, all these nuclear bomb exploding are not entirely healthy for the environment or for people who are living in nearby. So the decision was, let's not explode a stream of nuclear bombs in Earth's atmosphere. It's probably not a very good idea. So what type of nuclear propulsion NASA proposed? First, we'll explain a little bit how rocket works. Regular chemical rocket, it uses oxygen and some kind of rocket fuel, typically hydrogen, or it could be methane or something heavier. You put these two gases into a chamber and they burn, and because they burn, they expand and they are pushed backward. The most efficient chemical rocket engine that uses hydrogen and oxygen, the most efficient fuels. The gas are pushing toward the back at a speed of 4.5 kilometers per second. Thus, they are pushing the spacecraft forward. Now, if it was possible to push the gas faster, even faster than that speed, then the spacecraft will be able to travel faster and get to Mars a lot sooner, maybe in 3 months, maybe in 3 weeks. The two type of rocket propulsion that NASA is currently investigating is a nuclear thermal rocket. Basically, you have the spacecraft still use hydrogen, but instead of burning the hydrogen, there is a nuclear reactor that heat it to a much higher temperature, and because it's a much higher temperature, it's pushed through the back at least twice as fast, and therefore the spacecraft can reach twice as fast delta V, or it will be a faster spacecraft. Another option is do a nuclear electric, which is typical to accelerator. You need to have ions or some kind of gas that have electrical charge, and then using electromagnet, you accelerate it through the back and at a speed much higher than the speed that regular chemical rockets can do. And that's another way to push forward. And that's what NASA is currently planning as type of engine to move from Earth orbit to Mars orbit and back from Mars to Earth, and perhaps even going to the asteroid or further away in the solar system. This will be a much more efficient engine while you are already in space. And of course, the nuclear impulse engine that we spoke earlier on the Orion project. The image you see on the bottom is from an article from October 2020, a Seattle-based ultra-safe nuclear technology, USNC Tech. This is an engine they are developing, so it's recent in the news, so maybe in a few years there is a reliable nuclear engine that NASA can indeed use to send humans to Mars faster than using regular chemical rockets. So, what is the summary? What is my take? Currently, NASA does not plan to use artificial gravity in long duration voyages. They have the reason, some of it because there are other risks and other issues, and they want to being able to address multiple issues at one time, even if there is still some health risks for microgravity. My take is, why not? We can try to test such a technology, even if we don't solve all the problem. Maybe we solve one problem. We can travel faster, and have artificial gravity and maybe have some other mitigation to radiation. So why not have both? What did you think about this video? And thank you for watching it. And don't forget to subscribe and hit the like button. See you on the next episode.